Okay, can everyone hear and see me fine? Okay, so let's get started. What's on your minds?
I have a question about which derivations we need to know.
Which derivations? Okay, so let me bring up that sheet here.
I know that we have torque and capacitance, but in the notes it says there's a U-flip derivation and there's a creation of a field derivation.
Okay, so let me go through this here. Okay, let's see. So here, where's my cursor? Let's see if we can make it bigger. So this was one derivation. The torque on a dipole. So this was one of them. Then the flip energy, U flip is 2PE. So you would use that, but you will not derive that. You'll only the torque is the derivation. Not the derivation for U flip. U flip you'll use in a problem. Then let's see here. Summary. Okay, principle. Okay, so that seems to be the only derivation as such. You can have trivia questions about some of the theory, but that's like the actual derivation. No static. Okay, then here electric potential. So you have questions about the concept. That's not exactly derivation. Okay, this is the definition. KQ for a point charge. So you can have conceptual questions about any of this. I have an understanding of what potential is, potential energy is, but in terms of a derivation, let's see here. Where is the next derivation? So again, the concept of contours. So that's not a derivation. This is a derivation. The derivation of the capacitance of a sphere. So based on the definition of, so that's a derivation. This is a formula. The C of a sphere is R over K. So this is a formula that you derive. As opposed to capacitance C equals Q over V. This is not the capacitance of a sphere or anything in particular. This is the definition of capacitance. This is what a capacitance means, symbolized by capital C. Is the charge that you can store per potential. It's like the cross-sectional area of a tank, basically. How much water you can put for how much height. So this is a definition, but this is the derivation. So C sphere, just from the definition of capacitance, you have Q over V, but then you have a connection for V for a sphere earlier on here. You have, can you see my little hand moving around? It's a tiny thing, unfortunately. But that's KQ over R. So you substitute for V the KQ over R, and then of course a bunch of things cancel out. Mainly the two q's cancel out. You're left with r over k. So the bigger the r, the better, which is kind of obvious. If you have a bigger sphere, the charges are spread out, so you can put more stuff in there without building a height. It's like the garage with more floor space. You don't stack up. Yeah. So this is a sort of real life derivation. So those are the. Let me look again. I think.
Wait, I have a question.
Yeah,
Sorry.
go ahead. Yeah, sure.
So that is a derivation for the capacitance. That's a derivation, like the adding charges and everything. That whole the 3 paragraphs you have. Is that the derivation for capacitance?
Yeah, it's a one line derivation.
Oh.
So.
Okay.
I can't really see your mouse, so I couldn't really see which paragraph you were talking about.
Okay, what's the question? So she asked, like, what are the derivations that you could be asked? So those are two derivations. One is the dipole from I think the previous chapter, right? And then
the torque question, the
yeah,
torque one.
Yeah, huh?
Isn't that the torque one, the derivation?
Yeah.
The one with the triangle, isn't that one of the derivations from the previous chapter?
Yes.
Okay.
So yeah, so while we're here, yeah, let's kind of just finish off this business here. So this is the derivation of the capacitance of a particular shape. Capacitors come in many shapes. Spherical, and remember you can have two parallel plates, and that's for later. We haven't gotten to that yet, actually, Wednesday afternoon. But this is a capacitance formula for a particular shape, which is a sphere. And this can be derived. It doesn't like it fall from the sky like a law or a definition. It can be logically derived, which makes it a formula. And this is a derivation that could be asked. So you start with the definition of capacitance, and then for V, you substitute this thing up here. For a sphere, the potential V is the KQ over R. And then in 2 steps, you basically have the formula is R over K. So that's a derivation. And then you had a question about the other one, the dipole. So those are the only 2 derivations I can spot so far. I don't see anything else here that could be viewed as a derivation. There it is. Yeah. Okay. So this is the derivation, because the torque, it's not a law. It's not it's not a definition. It's a formula. If you put a dipole in a magnetic field, in an electric field, it tries to align with the electric field. There's a torque trying to twist the thing. This can be calculated, which makes it not a law or a definition. It's a derivation. It's a formula. So you go back to the basics of Physics 201. Hopefully you remember. Torque is R cross F, which is shorthand for RF sine theta. The cross is like a abbreviation for sine theta. So now R, if it's pivoting about this point here, R is the distance where you're applying the force. So that's just the length of the dipole, which is called d. So the dipole length is called little d. So R becomes the d. The force is the force, and you still have the sine theta. Next step, the force. Where did the force come from? The electric field, like a wind, is blowing this charge in this direction. So the force on a charge is the electric field times the charge. So the F became a QE, and then D times Q. This is a definition of a dipole moment. How strong is the dipole? The more the charge and the more the separation, that makes it a bigger dipole. So the dq or the qd you replace with p. And then again, pe sine theta, the cross is an abbreviation for sine theta. So we just proved that the torque is pe sine theta or p cross c. So this is a formula for the torque on a dipole. So when you turn on your microwave, the water molecules are getting twisted back and forth. That's what's happening. And so this is another derivation. And that was a derivation, what I explained. So as you can see, they don't make things very complicated. Each of these derivations, literally like 20-30 seconds, 1 minute tops. That's what it is. Similarly with the problem, these are not double dot problems where you do like 2-3 pages of calculation. In less than half a page, you should be done, quarter page even. So You really shouldn't be spending more than 2-3 minutes per question, so not more than 20 minutes total. So this was to answer what derivations could be on the test. So those are the two basically what I just explained. I am recording this, but I don't know how long it will take to upload it. So it's better if you anything you need, maybe write it down now. This won't get there in time, but I'll try anyway. Okay. Yeah. What's the next question? Anyone? Okay.
Can you do 16.55?
16.55. Okay, let me pull it up here. Okay. 16.55. All right, let's look here. And okay, how do I? It seems getting cut off. Okay. 16.55. Okay. $16.55. Okay, so what do we have here? An electric dipole P. So I'm going to write this down and then go to my paper and pencil. 16. Molecule is the electric dipole moment of P. P is equal to 5.3 10 to the minus 30. So I'm just writing this down. Coulomb meter. Oh, the electric field is 10 to the, is that 10 to the 4? 1 times 10 to the 4 newtons per coulomb. Okay. Times 10 to the 4 per coulomb. And what's the change in the potential? Okay, let me go to my paper and pencil now. Let's see. Oh, how do I? Okay. So here's the question. You have a dipole. What was it? It doesn't matter. Sulfur dioxide. Was that right? Whatever it was. Yeah, sulfur dioxide. Regardless, you have a molecule. Sulfur dioxide, so it's sort of more like a water molecule, but no matter. You can model that as a charge, minus Q and a plus Q on the two ends. It's separated by some distance, and you have two opposite charges, plus and minus. When you put this in an electric field, it's going to try to line up with the electric field. So suppose the red pencil is my electric field. Now, what did I ask? So you're going from parallel to anti-parallel alignment. So if you go from this to this, then this will rotate and try to realign with this. So you're flipping this dipole. So the U flip, if you go to the notes we just remember under that torque derivation there was a U flip. You don't have to derive the U flip because it requires calculus actually. But the U flip is just 2 PE. To flip it by 180 degrees from one side to the other. So they're asking you what the U flip is. So this is equal to 2 times, this is the proper unit by the way. They gave it to you in coulomb meters and the other one is in newtons per coulomb. So those are the official units, no conversion required. So this times 5.3 times 10 to the minus 30 times 10 to the 1 times 10 to the 4. I think someone's waiting to be admitted. Okay, and that would be it. If you manage to procure one of those simple calculators without graphing and memory and massive supercomputing capabilities, you can use that. If you don't have that, you would leave your answer like this, and that would be it. This is U. Make sure you have the units. What's the unit for this, by the way? Jessica, since you asked the question. They ask.
Well, I kind of forgot.
The unit for potential energy, kinetic energy, any energy, is the same unit. Any ideas, anyone?
Can't be dumb. It's force. Oh, it's force. Yeah, let me just forget. I think I'm too much in my MCAT.
Okay, so I'll let you guys figure this out. But anyway, you will put a unit there. And on the test, those calculators I bought for you, to lend you guys, they're supposed to come tomorrow, but most likely I'll leave home before they come. So for this test, if you don't have an official calculator, you would end it over here, put a unit, and call it a day, basically. That's it. Okay. Is this clear? Okay, next question.
Can you do 16.44?
16.44, okay. Ellie, do you have a camera on your computer? Do you have video?
I do, but I'm really just
Okay.
laying in my bed. And
Oh, okay. No, never mind. Okay, so excuse for privacy reasons. Okay, what did you say? 16 point what?
16.44.
44. Okay, yeah, okay. Okay, so let me go back to my this thing over here. Okay, 16.44. Okay, so let's all read this question here. 16. So you have three surfaces enclosing some electric charges. I see. 1, 2, 3, 4 charges. So it shows the three. Oh, no, I'm looking at the wrong figure. Wait a minute. Yeah, that figure belongs to 16.4. There's a figure above that problem. That belongs to problem 16.43. So ignore that figure. Yeah, okay. Or is that the, no, yeah, that's not it. Figure 16.35. Where is figure 16.35 though?
It's like you have to scroll up. It's on the other side of the page.
Oh, it is, okay. Oh, yeah, okay, I see, okay. Okay, so there is the figure. And, golly gee, what a complicated figure. It looks like these unicellular animals, paramecium or amoeba or some such thing. What the heck are they doing in here? All right, let me read the question first, and then we'll look at this figure. It shows three surfaces enclosing some electric charges. All right. Which surface has the greatest net electric flux emerging from it? All right. So I'll put this down here. So this is a 16.44. So A, most 5. Okay.
Hey, Doctor, could you have a
Yeah.
question?
Yeah.
So, since we already had 16.39 on the quiz, I thought you told this section would not be covered on the exam. Wouldn't be one of the tested questions.
No. The section can be. The same problem won't be repeated.
Oh, okay. Because I remember during the last review you told we wouldn't have this section.
Okay. No. There was some other section. Let me see which one. Oh, okay. Did I? Okay. Did I say that? Let me see what is the section there. No, so this was on there. So yeah, so what I said was, where is my hand? It's hardly visible. This foolish thing. All right. So in this section, 16.48 and beyond will not be on the test. Okay, so those two double dots will not. 16.48, that's actually the derivation for the derivation for the parallel plate capacitor. We'll get to that later. So 16.48 and beyond is not on this test. So you have the first 5, 6 question through 16.47. So those are in principle a fair game. Okay, so this section is there partially. But let's see. But these are not hard things. Okay, let me write down the question. Most flux. Okay. B. Which surface has the greatest net inward flux? Okay. So B. Phi in. Okay. And C. So many parts there. And does any surface have zero net flux? Okay, zero. Okay. So now let's look at this figure here. Okay, so the first is the most flux. Gauss's law tells you that the flux leaving the surface equals the 4 pi k times the charge inside. That is proportional to the charge inside. So the more the charge that's inside any closed surface, the more the flux that's going to exit that particular surface. So here, if you look at this surface over here, right? It's called surface 2. They named it. That's surface 2. This paramecium like thing. Okay, so here you have 3.2 plus minus 6.7. Okay, so what is that? That's minus 3.5. So let me write down the charges. So for a surface 2, the Q enclosed is equal to, what did I just say, minus 3.5. So let's go ahead and write down the charges for all of these. So for a surface 1 has, what does it have in there? It has the plus 6.7, so 6.7. The 3.2 is also in there, plus 3.2. And it has the minus 6.7. And it has a minus 3.2. Okay. And surface 2, which is surface 2. Oh, no, I began with surface 2. So now surface 3. Surface 3 has it has a minus 3.2. Then it also includes plus 3.2. And it includes a plus 3.2. So make sure you have here, let me go to my paper for an instant here. So this is what I have. Surface 2, which I began with, has a minus 3.5. Surface 1, 6.7, 3.2, minus 6.7, minus 3.2. The 4 charges inside surface 1. Surface 3, you have minus 3.2, 3.2, 3.2. So this is equal to 3.2. This is equal to 0, and that's minus 3.5. Okay, so let's go back to the figure now. So indeed, surface 1 has 0 charge inside. The flux will be 0. Surface 3 has the most positive, so the most exiting flux will be from surface 3, 3.2, and surface 2 is minus 3.5, so it'll have inward flux. Let's go back to that figure so you'll see what I'm talking about now. Okay, so let me go back to my hand over here. Okay, is this making sense? Are you able to relate to what I just said? So like surface 2. Okay, yeah. So surface 2 is this this thing over here. Is going from what, like 4 o'clock to 10 o'clock or some such thing. There are only 2 of those dots inside, 3.2 minus 6.7. That gives me minus 3.5. So that's basically what you do. Surface 1, it has 4 of those dots inside. Just add them up. So that's the procedure, and that leads to this. These are those sums over here. Those are the things. Here I already added the 2 things. But now to go back to the question. What was the question? So the question is somewhere else on the page. This was it 6.44? Which one was this?
It was 16.44.
I mean, yeah, 16.44. Okay. So let me get there. Okay, 16.44. So which surface has the greatest net electric flux emerging? So that would be this one. So this is the answer to A, most flux, because in magnitude now you can see this. Okay, actually I wrote down the questions. I forgot. Yeah, I wrote down the questions. Okay, so A, the most phi E. So in magnitude, the 3.5 is more, but usually exiting is positive. So this is more in that sense. This is more in magnitude. Next question, which has the most inward flux? That's B. So that would be inward flux. This is the answer to B. And then is the flux through any surface zero? So the lines going in and lines going out, are they canceling? Yes. This would be C. As many lines are leaving as they're entering. So the flux over here cancels out. There is no net charge inside. The plus charge and the minus charge, they cancel each other out. So there is no total. These are what I calculated here is not the flux. I calculated the charges, but the flux is proportional to those charges. Okay, any questions about this problem we just did?
Can you explain like what inward flux is again? Sorry, I just forgot.
So flux, let's go back to the theory here. So here, so that was, which that's, was it here? Here we go. Yeah, so if you look at the summary for this chapter 16, lecture note 1, here is the flux. So the flux is, that's electric flux is E dot A. That's EA cosine theta. And then, so the dot is is abbreviation for cosine theta. And then Gauss's law makes a connection between that flux. If you have a closed surface, that's equal to 4 pi kq. So k is the 9 times 10 to the 9. That'll be provided to you. And times the charge. So hence the proportionality between the flux and the charge. 4 pi k is a constant. Okay, is this clear?
Yeah, that helps.
Sure.
But so inward flux is just like negative charge. Is that what you like? Is that I'm just like I'm like confused on the definition of like inward. Like I know what like flux is, like how to solve for it.
So the surface for a closed surface, remember the surface, it can be represented as a vector. You put a toothpick into the pancake and now you turn it into a pointy thing. What used to be flat has become pointed. It becomes an arrow like a vector. For a closed surface, the arrow is pointing outward.
Okay.
So if you have a positive charge inside, the electric field is pointing outward. So it's along the direction of the area vector. So so the angle is 0 and cosine of 0 is 1. However, if you have a negative charge inside, the electric field is pointing inward. Now, now the electric the area is pointing outward. It's outward is positive. So E is going this way. So the angle is 180 degrees. Here, it's 180 degrees. A cosine of 180 is minus 1. That's why the flux ends up being minus if you have a negative charge inside. It's not just A times A. You have a cosine theta, and that's where the sign is coming. So outward electric field is positive because that implies a positive charge in its belly, and if the closed surface has a negative charge in its belly, the electric field is pointing in. It has an inward flux. So that's the connection between the sign and the direction of the field and the flux, basically. Okay, any other questions about this 16.44, I think? Okay. So let me. Okay. All right, what's next? What else?
Can you do 16.65?
6.5 you said, Anna?
Yes.
Okay, 6.5. Okay. Okay, so let me draw this so then I can go to my paper and pencil. Let me write this down. 4 charges, you have 5 coulombs, so place at the corner there. 30 centimeters on the side, 2 charges. Other 2 are negative, okay, so yeah. Let's see, diagonally opposite each other are positive, all right. Q4. Uh, 30 centimeters. 30 centimeters, okay. And that's it. What's the magnitude in the direction of the force on one of the charges? Okay. So I assume that's the total force. Okay, so F. They want the direction too? Yeah, okay. Okay. So now I will go to my paper and pencil. Okay. Okay. So here is what you have. Okay, I need more paper. Okay, and this was 16.65. So you have a square arrangement of charges, and your 4 charges, they are equal in magnitude. And what are they? 5 microcoulombs. Okay, so each Q. So this, for example, Q4 is equal to, where is it? Yeah, 5 microcoulombs. Okay. So anyway, so all of the charges, they're the same in magnitude, but the ones along one diagonal, they are negative. The ones along the other diagonal, they are positive. And you are asked to find the force, for example, on Q4. It doesn't matter which one. What is the force and what is the magnitude on this force over here? Okay, is the question clear, everyone? Okay, so you have 4 charges and you're trying to find. So this would be an example where you can use Coulomb's law. You just calculate the force from the other 3 on here, and so you will add them up vectorially. So the law, you have the law of superposition of electric forces, that if you have multiple forces, you can add them. You could also calculate the electric field from each and add the electric field. It doesn't matter how you do it. So the F on here, F, the F you're trying to find, this is going to equal F of 1 on 2, 1 on 4, plus force of 2 on 4, plus force of 3 on 4. So these are the forces. The force on charge 4 caused by the first charge, the second charge, and the third charge. So the commas are separating the 2 things between which there is a force. So now each of these forces, the magnitude is given by Coulomb's law, K, Q1, Q2 over R squared. So those are the magnitude. So now next sheet of paper here. So you have the magnitude F14 is equal to F24 is equal to F34, and that's equal to K. All of these are 5 microcoulombs. So it's K Q1 Q2 over R squared. So it's just 5 times 10 to the minus 6, and then times another charge which is also 5 times 10 to the minus 6 kq over r squared, and over the distance r was 30 centimeters. Yeah, there it is. So 30 convert to proper units. So our standard unit is a coulomb. So 10 to the minus 6 gets rid of the micro. A microcoulomb is 10 to the minus 6 coulomb. And the distance is 30 centimeters. Bad units change to meters. So this is 0.3 squared. Okay. So this is the magnitude of each. So these are the magnitude. Okay, is this clear, everyone? Any questions?
So
Oh.
you have to add that 3 times to get the total force on Q4.
No, so you cannot add the magnitude because these are vector quantities. There's a direction. You have to add them vectorially. You have to add them. So they are vectors. Vectors can be added. 2 plus 2 doesn't give you 4 with vectors. So if this force over here, I can, by the way, I can show the directions of the forces. There's a force in this direction. This is F of 2 on 4. The negative is going to pull on it. This negative will pull on it. This is force of 3 on 4. Right? And then this is going to repel it. So here you'll have a repulsive force of F of 1 on 4. Those are the 4 forces. So with vectors, because you have angles between them, you have to add them vectorially, which means you break each one into its x and y component, add the x component, add the y component separately. Those will give you the x and y components of the total. And again, there's not a simple connection between that and its magnitude. So you have to apply the whole vector machinery to this. So how that pans out, we're about to see. But yeah, so be careful about vector. So all of you guys, you should either today or even after the test, make sure you watch my physics 201 recap video, recorded video that I have. So it goes through all of that, because if you're many of you notice I'm missing the basics in terms of what to do with vectors and stuff like that. But so these being vectors with the bars on top, the bar tells you cannot add them. It immediately prohibits you from adding them in an algebraic manner. You have to add them vectorially. So these are just the magnitudes, and now you have to break them into components. So you have the following. You have f of f total x. This will equal f1 4x plus f2 4 x plus f of 3 4 x, and that's it. So these 3 forces shown in the pink or almost red, those are the directions of those forces. They cannot be added as numbers. They are vectors. You have to use a special mathematics for adding these. So now each component is equal to the magnitude times cosine of the official vector angle. Okay, so this is equal to f1 4 cosine of theta for 1 4. Each vector has a separate angle. All of them are different. Then plus force of 2 4 cosine of, oh, it's going out of view. Cosine of theta for 2 4 plus f of 3 4 cosine of theta. No one's waiting to be admitted, right? Yeah, okay. Of 3 4. Okay, you see the machinery of the vectors? This is how vectors are to be added. You cannot add the magnitude. So you have to do it component by component. The x component is the sum of the x components of what you're adding. Each x component is the magnitude times cosine of theta. Now let's look at those angles. So you have, these are the angles. So let me draw some axes. So here's my x and y axis. Okay. So on here, f of 1, 4 was like this. Do you see this? This is from before. See?
I have a question. So
Yeah.
how do you know like the angle's going like down that way?
Here, look at this. This positive will push on this positive, right?
Oh, yeah.
Now the rule is you have to move the vector so that the tail is at the origin. So I just moved it so that the tail is at the origin. Okay. So before you evaluate anything with vectors, move the vector so that the tail is at the origin or at the xy, the conjunction of x and y. Okay, is this process clear so far? Any questions? Anybody? Make sure. This applies to many things, not just electric forces. You'll be encountering many different types of forces, and also going back to physics 201, which you'll need for other purposes. And this is how vectors work. So you have to be rock solid with vectors to sort of succeed at many other things. Okay. So that's that one. Now look at the other forces now. Here is F. There is F214. It's going straight up. You see, it's heading for the sky. So this is my F. What is that? 24. And then the last one is going to the left. Do you see this one? F34 is going to the left like this. So this is F34. Yes. Any question? Anybody? If anything is the slightest bit suspicious, let me know. Don't suffer in silence. Okay. So now for the angles. So this is the theta for a 2-4, and that's 90 degrees. Just from looking at it, that's 90 degrees. Then here is the angle for 3-4. It's going to get crowded, but anyway, this is the angle for 3-4. This is the theta for 3-4. And you can notice that it's 180 degrees. Okay. And then finally we come to which color have I not used? The blue. Okay. You go like this all the way around. So this is theta for what is that? 1-4. Okay. Is this completely clear so far? This was a good example to do. It kind of runs you through the whole vector process, which you need. You'll be needing it throughout this whole semester now and then. Okay. So this, what does the angle look like to you? You want to take a guess?
Would we do 360 minus 45 degrees?
Exactly, right, exactly. So if you went around the whole way and came back here, that's 360. But then you back off by 45 degrees. So that would be 315 degrees. Okay, is this clear so far? And now you put these angles into where they belong. So this is the 315. Put that in there. And then what do you have? 3-4 is this one here. Jump over that one. Okay. Notice how the arrow jumped over the other one without hitting it. It's sort of like a flyover. And then which is the last one? The green one. That's a 2-4. That goes in there. So now we are ready to and the magnitudes we found earlier. That's that 5 k times 5 times 5 0.3 squared and all of that stuff. Okay, so we can actually solve for that at this point. Why not solve it? So here, let's go ahead and find a magnitude for this. Okay, so let's go ahead and do this. How do I? There it is. Okay. So let me go ahead and crunch this out at this point, because the numbers become very sort of bulky. Sometimes it's good not to leave it in symbol. Just go ahead and crunch it out, because you'll have something more compact. So what was that? So k is 9 times 10 to the 9 times 5 e to the minus 6, the whole thing squared, and over 0.3 squared, over 0.3 squared. Is that right? Looks okay. 0.3. Yeah. So see how compact that answer is? 2.5. This is 2.5 newtons. So now we can put that in here. So proceed with this. So fx. So we are working on this equation. The f of x is equal to. We are just putting in all these angles, and 2.5 will go into the magnitude. So f of x will equal 2.5 a cosine of what was this? 315 degrees, and plus 2.5 again, cosine of what was that? 90 degrees, and then plus 2.5 cosine of the last one. Where is it? 180 degrees. Okay, and that's it basically. So you crunch this business out now. Okay, so a cosine of 90 is 0. A cosine of 180 is minus 1. And cosine of 315, let's put that in here. Cosine of 315. What is this? Which is the same as 0. Square root of 1 over square root of 2. Yeah, so this is equal to 0.707. So those are those cosines, right? And now let's crunch this baby out and see what happens. So this is equal to. So that's equal to 2.5 times. So you have 0.707 plus 0 and minus 1. So plus 0 minus 1. What is this? So okay. So it's minus 0.7 minus 0.7325 newtons. So that's the x component. Okay, is this clear, folks?
I have a question
Yeah, go ahead.
about the magnitude of these forces. I'm wondering how, like, if all the charges are in your original drawing, they're 4 corners of like a square.
You're right. Yeah. So they're actually not equidistant. Yeah, excellent point, by the way. Okay.
So would they have different magnitudes?
They will have different Yeah. You're right. So very good observation. So here, these charges are not equidistant actually. So this is 2 point. These are 0.3 meters away. But for F14, the magnitude is farther away. It's along the diagonal. It's not 0.3 away. Okay. So you're right. So for so these forces here, Okay, very good observation. So for the only one which is out of line is this. So this is true for those the negative charges which are above and to the left over here. But for the other one, you're right. So that's going to be, what will you have instead of 0.3 squared? It's going to be the diagonal of that of that square. So this is 2.5 for this one, and let's find the magnitude. So 2.5, which is which over here? The only one that needs to be fixed is 1,4. That's the very first one over here. So okay. So here's an aside. So F14, this will equal K of 5 times 10 to the minus 6 squared over that distance is going to, the square of that of a hypotenuse is equal to the sums of the squares of the other two sides, the adjacent and the opposite. So it's going to be 0.32 squared. So it's going to be double, the square is going to be double. The distance is square root of 2 more. So this is going to be 0.3 squared plus 0.3 squared. Okay. And so the distance is square root of 2 times that. So this is going to be, that force is going to be weaker. It's going to be half of what you had before. So this will equal not 2.5, it's going to equal 1.25 newtons. You're absolutely right. So for the diagonal force, it's actually half. The distance is not double, the distance is square root of 2 times, bigger, but you square the r, so it ends up becoming double, the square is double, so the magnitude is half. Is this clear? Any questions about this? Okay, so timely rescue. Yeah, thank you, Ali. Okay. So now, so here you will put 1.25. And so now, let's go back to the calculator here. So where was that? So, yeah, okay. So 1.25 times 0.707 and then minus 2.5. Okay, so 1.25 times 0.707 and then you have 0 and then you have minus 2.5. So this is now equal to minus 1.62. Evidence that my sugar level is starting to drop. So this is, what was it, minus 1.62. 0.62 newtons. 616 actually. But the 3 digits, so that's the thing. So this is just the x component. Okay, any questions? Okay. Now you have to, yeah, go ahead, yeah.
So a question like this wouldn't be on the exam because this takes more than like 10 minutes. Because you said each problem should take correct. Yeah, I when I saw the problem, I was initially somewhat tempted to just tell you this is beyond the scope of the exam. However, this is a good training ground. See, people got some reinforcement with the vectors, how to
find components and things like that. Even if you have two charges, you still have to you still have to find components. If they ask you for the magnitude and direction, instead of four, even if you have two charges, they could be at an angle. What is the direction of the force? So many people need some revision with the vectors and all. So I think it is worth doing just for that reason. But yeah, you're absolutely right. I completely agree with you on that. So this is minus 1.62. So for the training, it's good to do something that's harder than the actual event. So that's that. And then f of y, it'll be the same thing. It's the same equation you had over here with the x component. Replace the cosine theta with the sine theta. So it's exactly the same equation. So you'll have, but you have sine theta. Okay. So you have 1.25 as sine of 315 plus 2.5 sine of 90 plus 2.5 sine of 180. And now sine of 180 is 0, sine of 90 is 1, and the sine of 315, most likely that's also a 0.707, but this is sine, so it's going to be minus 0.707, but let me just, given that my brain seems to have stopped for the day, let me just put this in here. Should be minus 0.7731315. Yeah, minus 0.707. So this is 0.707 with a minus sign. So now this is equal to 1.25 times minus 0.707, and then plus plus 2.5 times 1, and then 0. So that is equal to, let's see here. Okay, 1.25, 0.707 minus 2.5 minus of that. So it's going to equal plus, looks like. So this is equal to plus 1.616, 1.62 newtons. So these are the x and y component. So the force is equal to the x component was, what was it, minus 1.62, and then the y component is plus 1.62. So this is a vector which kind of looks like this. Yeah, so this was a very good, vector practice actually. And so, so the x is negative, so you're over, and the y is positive. So you're basically over here. This is the second quadrant. This is the first, second, third, and fourth. These are the fourth quadrant. Can everybody see that? The x is negative, so you're on the left. And then the y is positive, so you're up here. You're somewhere over here. They are equal. Aside from the signs, they're equal. So that force is exactly in the middle. It's going to be 45 degrees from here and here. And so the official angle, the theta for this total force, the net force, that theta is going to be 90 plus 45. Okay, 135 degrees. So that's the angle. They were asking for the direction of the force. So it's going to be like this, which is not surprising because you have that one charge over here was pulling it up, one charge here was pulling it this way, and that corner charge, the positive, did its best to push, but it's not going to, win against those two other charges. So you end up with a net force in this direction. So that's the angle. And as far as the magnitude is concerned, F net magnitude, so that's just F net without the sign, that's equal to x squared plus y squared square root. So this is equal to 1.62. So that's equal to F net x squared plus F net y squared square root. Okay, is this clear, everybody?
I have a question.
Yeah, sure.
So, if it was not plainly obvious that the direction was 45 degrees in the second quadrant, would we have to solve that using like cosine and sine and tangent?
Right, yeah, good question. Yeah, so let's do it that way. So here, this is like a semi-intuitive way of doing it. But the beauty of the physics formalism is if you use the theory to the, and allow it to reach its natural conclusion, no thinking is ever required. You never have to make a judgment and make a decision. Let's do it that way also. So let me kind of just complete this thought. So this is equal to this is equal to 1.62 minus 1.62 squared plus 1.62 squared, all of this. So it's square root of 2 times that, and so this will equal, since, might as well finish this whole thing. So this squared, so 2 times this squared, and then square root of the whole thing, square root of this. So that's equal to 2.29. So this is the magnitude. That's how strong the force is. The net force. So this is a combination of the 3 forces. One is pushing, 2 are pulling, and the pulling wins because there are 2 of them, and also they're closer. Now to answer your question, yeah, very good point. So that the theta, the rule is that the theta is arctangent of the y over the x. And then plus 180 degrees. Okay? So this is the rule. You see how beautiful and perfect and complete the theory is? You don't have to think about, let me get rid of this calculator here.
And it's only 180 degrees because it's in the second quadrant, right?
The second and third quadrant. So for 2 and 3. If it's over here, it is in the second quadrant, by the way. But if it's in the second or the third, you add 180 degrees. You see how complete the whole theory is? No thinking required. Now let's just crunch it out and let it reach. So you don't have to figure all this out. Oh, look, it's between this x and the y, it's on the left. Nothing is required. So here. So now you have arctangent. So yes, in this case, do add it. It is in the second quadrant. And so therefore, the tan inverse of, what were they? Minus 1. Plus 1.62 over minus 1.62. So here is this, right? And then yes, plus 180 degrees. So arctangent of plus 1.62 or minus 1.62, I can do this in my head. So this is equal to minus 45 and plus 180 degrees. And that's equal to 135 degrees, same as before, see? So you see how the formalism is absolutely bulletproof, it's waterproof, watertight. You never have to figure anything out. No. If you really understand the theory and use the formal procedure, ideally you should be able to shut your brain off and let the thing take its own life, basically. It has a life of its own. So once you set up everything and just follow in a completely unthinking and dumb way, you just follow the procedure, you get the answer. If you ever have to think and be creative, that means something is missing from your understanding of the theory. If you know the theory, no thinking is required, basically. It's an automatic process. Okay.
So if there was only 2 charges, the direction would just be attractive or repulsive.
Right. It's going to be along the line of those 2 charges. So you would need to have at least 3 charges where you'd have to do any of this. But you could have 3 charges. You had some simple homework problems with a triangle, I think, one time. Either homework or in classes or something. It rings a bell. But we had something less fancy than a square, that's for sure, at one time. So you could have something like that. But to answer size, comment, a problem of this complexity will not be on the test. But this was a very good training example, excellent choice. And I will scan these sheets and put them on the website. That'll happen within 15 minutes. That video upload it'll go into early morning most likely. I think there's no way around it. Even if I skip the captions, I skip the rendering, just the upload will take 6 to 8 hours. So maybe less, who knows. But
Would you do 16.34 if we're good on this one?
Okay. 16.34. So let me number these so they don't get mixed up. Let's see. So this was the first one, I think. 1. Put 2 over here. 2. 3, okay. Do you say 16.34? 34, okay.
Yeah.
Okay. Oh, you can't see this, okay. 34. Oh, okay. All right. Okay. So let's wrap it up after this. The 16.34. I think my brain is signaling me to go get some food. Or starting to make mistakes. Okay. Okay. So let's all read this question. A tiny ball of mass 0.5 grams. Nothing like a tiny ball to bring an end to the festivities. Okay. It's like the ball dropping on New Year's Eve. Okay, so a tiny ball, mass is 0.5, so I'll just write this stuff down so we don't need this. So this was 16.34, 16.4, okay. The ball mass is equal to 0.5 grams, all right. It is tiny, 0.5 gram, half a gram. It's suspended by a thread of negligible. Is there a figure that goes with it? There is, yeah, okay. Yeah, the figure right below. Oh, okay, that makes it easier. And then what else happens? There's a horizontal electric field of 400 newtons per coulomb. Okay, E 400 newtons per coulomb. All right. Then if the ball has a charge of 9 microcoulombs. Okay. What will be the deflection angle of the string measured from the vertical? Okay, angle. Excuse me for a second. Hello? I'm in office hours now. Yeah. Okay. Okay, I'll call you later. Yeah. Okay. So let me draw this figure here. So let me turn off this display and go to my paper and pencil. Okay, so this would be sheet number 4. Okay, and so here are the numbers. I wrote them down. That's the mass, electric field, charge, and this. And the situation you have is, I can still see this like this. That's the theta. This is Q. So that's basically it. Okay, so you have a little ball tied by a string to the ceiling, and then if you blow on something, it's going to get pushed to the side. That's what's happening. Think of the electric field like a wind that's blowing on this charge. That's going to get pushed this way. Is the charge positive? What does it say? It's electrically charged. Oh, you're supposed to find the charge. Okay. So the question is, what is the charge? Okay. Now the electric field is to the left, and the ball is getting pushed to the left. That immediately tells you that the charge is positive. It's going the same direction, because you have the following relationship. You have F is equal to E times Q. This is a vector equation. So the force picks up the direction of the charge, picks up the direction of the electric field. If Q is positive, it's the same direction. If Q is negative, it's the opposite sense of direction, the same line of direction, opposite sense. So F is equal to E times Q. So remember, this is a vector equation. All the components of E get carried over to the F, multiplied by the Q. And so now you have, so that's the electric force. This is the electric force. So the electric force is this way. And then, so this is an example where I'm summing all the forces. So to solve, again, watch my Physics 201 recap video, even if you do it after the test. So if you understood that, then this would be basically, it kind of leads into this. It gives you the background of what to do with force summations and stuff like that. So this is a Newton's law. Huh?
I just had a quick question.
Yeah.
Is it asking for the charge on the ball or the deflection angle? Or is that?
No, it's asking for the angle.
Okay, yeah. Okay, that's good.
Okay, yeah.
Okay, sorry.
It takes 2 minutes to do this. So it's asking for the angle. So this is a Newton's law type of a problem. You have multiple forces on it. They're adding to give you mass times acceleration. There is no acceleration. It's basically peacefully hanging in the wind at this constant angle. So the A is 0. So all the forces add up to 0. So you have the following fact. Oh, so no interruption. Okay, so all of the forces add up to give you mass times acceleration, right? So this is Newton's law. So the first thing is to notice all the forces. So you have two field forces. One is the electric, the other is gravity. The only thing that's touching it is the string, so you have a tension force. So this is the tension force, F of T. So those are the three forces. So they add up, again, vectorially, they add up to give you 0. Vectorially, they add up to give you 0. So now the same thing as before. You have sigma F along the X is equal to F electric, X component plus F gravity, X component plus F tension, its X component. And the same for Y. So this is equal to the magnitude times the cosine of the angle. So, and this equals 0. There is no acceleration. Okay. So the acceleration is 0. X and Y, both components are 0. So sum of the forces, X component, this equals 0. Okay, is this clear to everybody so far? Any questions? Okay, sure. Okay, so now so now just continue this thought. So this is equal to each x component is the magnitude times the cosine of its angle. So the electric force, we have it up here. The magnitude, this is equal to E times Q. And cosine of the x component, look, it's minus it's 180 degrees. It's to the left, right? So the theta for the electric force is 180 degrees, is opposite to the x-axis. Is this clear, everyone? Okay, sure. Okay, so this is 180 degrees. So I'll redraw this down here. Let me draw a cleaner figure. So here is the x, and here is the y, and this is the electric force. And here's the gravitational force, and there's the tension force. So these are the angles. This is theta for the tension. This is theta for electric, and that leaves gravity. That's theta for gravity. Is everybody okay with these angles? Yeah, okay. So a theta for gravity is 270 degrees. A theta for electric is 180 degrees. And this blue thing here, isn't that the question? Or yeah, that is the question. This is the whole question. What is this angle? Is that right? They ask you for the angle, or they give you the angle? 16.34. Let's see, what did they give you and what did they ask? They gave you the E, they gave you the chi. What's the deflection angle? We are on 16.34, right? Yeah, so that's the question. What is this angle? Okay, is this clear so far?
I have a question about the angle.
Yeah, right.
Since it's like hanging, wouldn't the angle be different? Like, wouldn't it be the top angle of the triangle and not the bottom one?
So the angle is always between the x-axis and the positive direction of the vector. So here the vectors we are analyzing, they are the forces, right? So it's not this angle necessarily. I think I know what you're saying. That the final thing that they're looking for is this theta here. Is that what you're saying, Ellie?
Yeah, that was what I was wondering.
Correct. So let's call this theta. What shall I call this? Theta. Let me call this theta 0. Okay. Yeah, you are right. Okay. So, but we need to find this to find that theta 0.
Yeah.
Okay. Yeah. Right. So yeah. So we need to find this, and that you're right. So that won't be the answer, the final answer. But we need to find it. And then 90 degrees minus this, that's going to be the theta 0 that they're looking for. This is theta t. This is theta 0. And then this is 90 degrees. And so theta 0 plus theta t is equal to 90 degrees. So we have to find this, and then 90 minus this one will give you the theta 0. Is this okay?
That makes sense.
Okay. Yeah, okay. So right now I'm kind of just laying down our immediate goal. So we have to solve for this. We are going to use the vector equations cannot solve for the theta 0, because that theta 0 doesn't figure into the x and the y component. But so we have to find this theta first. So this is the angle of the vector, the official angle, and that is not the theta 0 that they showed in the figure. 90 minus this angle is going to be theta 0. So the first step, we want to find this one. Okay, is everybody okay with this so far? Any other questions or comments? Dakota, are you okay? Am I confusing more than you were before? Okay. The net improvement, all right. Okay. So now, where were we? So here's that equation. So back to this. Each of the x components is the magnitude times cosine of the official angle. And this was the point. The first force is the electric force is E times Q based on this equation here. Cosine of its angle is 180 degrees, the orange one over here, right? Going like this. Okay, then the next one is the gravity. So plus the magnitude of the gravitational force is the weight mg, and cosine of it's 270 degrees. See the pink one here, 270 degrees. And then the last one is the tension. So that value is T, and cosine of theta for T, which you don't yet know. And this whole thing is 0. Is everybody up to speed so far with this? Okay. So let's go ahead and crunch out a few things. Cosine of 180 is -1. Cosine of 270 is 0. And this cosine we don't know. So let's so just continuing with this. So you have f x. Yeah, sum of all the forces. So sigma of x, this is equal to minus EQ plus 0, and then plus T cosine of theta T, and this whole thing is equal to 0. So which means that cosine of theta T, this will equal, what does it equal? Bring it to this side, is equal to EQ over tension, and this is equation 1. So we haven't solved it yet. We only did it for the x. Now we have to do the same process for the y. Is everybody okay with this? Okay. Now repeat this for the y. So for the y, the sum of all the forces along the y, that's equal to the same equation with sine theta. So that's equal to EQ sine of 180 degrees plus mg sine of 270 degrees plus t sine of theta t, and that whole thing is equal to 0. And so put in the value. The sine of 180 is 0. The sine of 270 is -1. And then we don't know what this one is. So rearrange this. So you have minus mg plus t sine of theta t. This is equal to 0. So move things around and solve for sine theta. So therefore sine theta of t, that's equal to mg over t. This is equation 2. Okay, is this clear, everyone? We are getting close to the grand finale, so make sure that all of this is okay. All right. So now we want to find theta. So divide, let's convert the sine and the cosine. If you divide the two equations, you will get the tangent of theta, and then you can find the arctangent, inverse tangent of theta. Okay, so now so divide, take equation 2 and divide by equation 1. Okay, and so that then gives you, upon doing that, what happens? You'll have a sine theta of t, divide the whole thing by the other one, cosine of theta of t. This is equal to mg over t and EQ over t. Right? Is everyone okay with this? Yeah? Someone
I
feel
have
it?
a question.
Yeah, go ahead. Yeah.
Do you have this type of question like on the exam? Because this would take at least like more than like 6 minutes.
Right. So again, no, but it sort of gives you good practice through many different things. You see.
Okay.
Yeah. So it's good, like that other one with the square and those four charges. But the point is, this is good training. It puts you through your paces and gets you ready. So it's still worth it. It's a good revision of everything. And so now,
And then,
yeah,
sorry, one more question.
yeah.
Any of the questions we do right now won't come on our exam.
Oh, they could potentially if they fit the bill.
So you
But these are complicated. But I mean, as a general policy, there is not a rule. The rule is any question that you had on homework and any in-class examples I did, premeditated examples, those will not be on the test. But during this office hours, if you ask me a question, you could get lucky, and that could be a question that's on the test.
okay. Since you already
That's a possibility. But these are kind of more frightening than the question needs to be. But in fact, yeah, there is no policy that a question asked during office hours cannot be on the test. So that's not true. That's not. There's no such policy. Okay, we are now on to the sheet number 5. So. The alarm's going off everywhere. That's a reminder for me to take the trash out. Tomorrow is trash pickup day every Wednesday morning. The bag will sit there until next week. Okay, so now sine over cosine is tangent, right? So you have tangent of theta t. That's equal to, notice by the way that these two t's will cancel each other out. So that is equal to mg over E times Q. And that's equal to what? Mg over E times Q. Where are those numbers? I wrote them down somewhere. Okay, I can look at the problem again. So the mass was this tiny 0.5 grams. So make sure you use the official unit. See, everything that we discuss here is good practice for any problem that you do, because like parts of this will be relevant. So it's something as simple as converting the unit. So that is 0.5 grams. So it's actually 5 times 10 to the minus 4. It has to be in kilogram. Times 9.81 over the electric field was 400. No, that's the wrong problem. 400 newtons per coulomb. Newtons per coulomb is the official unit. So just leave it like this. And times the charge was what? 9 microcoulomb. So microcoulomb is not the official unit. Coulomb is the official unit. So convert 9 times 10 to the minus 6. And what is this? So calculator again. Whoosh. Okay. So we have what is this? 5 e to the minus 4. 5 times 9.81 divided by 400 times 9 to the minus 6. Okay, and that seems to be what? 1.36. Okay, so now that's the tangent. So the theta t is going to be the arc tangent. So theta t. By the way, notice that all of the numerator and the denominator, everything is positive over here. So that's the first quadrant. So do not add 180 degrees. So anyway, so this is going to be arc tangent of that number, and then plus 180 degrees. So no, because it's in 1. It's in quadrant 1. Okay, so let's find this. What we have here. arctangent of that is what? 53.7 degrees. Now, as was pointed out correctly earlier, this is the theta for the tension. That's not the angle that they're talking about. They're talking about the angle from the ceiling. Remember going back here? See, this is the theta t. They want this theta 0. That's going to be 90 minus this 53 degrees. So the theta, so this means that the theta 0 is 90 minus 53.73. Okay, and so what is that? Dakota, do you already know the answer in the book?
I do, yeah. It's
Is it close to this?
oh wait, let me find it. I had it pulled up. It's
Okay.
36 degrees, yeah.
Yes, okay, yeah. I was going to say at this point, if it doesn't agree with the book, shoot the book or the author or something like that. But okay, it's a good thing that it did agree. So, but that's to bring a very long story to a happy ending. It could be in one of those Hallmark movies, basically. You have a happy ending.
I feel like any of the problems that require like vector addition take like a decent amount of time.
Not
At least from the
right, not necessarily. Here you had you had three forces here. That's what made it complicated. And then you weren't given the tension. So suppose they gave you the tension, you would not have so many steps. If you knew the tension, we could have solved it like halfway back. Doing just the x equation or y equation, you could already solve it. But you have two unknowns. You don't know the angle and you don't know the tension. So you have to do the x, you have to do the y, and solve them simultaneously and all of that. You see the point? That's what made it complicated. So you can have components, and it doesn't have to be quite this long. Remember too that I'm explaining it, so it takes longer. I'm writing like all kinds of intermediate steps and I'm explaining it. When you're doing it on a test, you're not trying to teach the instructor. You're trying to prove that you know what you're doing. So it's always longer when I'm doing it, when I'm explaining the solution, than when you actually do it. If I were to do this, I would do it in like 3 lines, 3-4 lines, very fast. I won't be. I would just jump to it, I wouldn't write both the symbolic version, all so many things, and this diagram and this and that and so forth. Some of the stuff can be skipped, not all of it, but and when you're I'm trying to speak at a somewhat slower pace so that people can understand me, and using colors and all of these things. So you try it. You'll see. You try to do it. It won't take more than 3 minutes. Even this one. But the problems on the test will not be quite this complicated. But what I'm saying is, even in the word, this will not take 10 minutes. It's taking 10 minutes now. But yeah, when you do it yourself, it won't take as long as it did right now. And you can even check it. That's the thing. Okay, is this clear? So I think we covered quite a bit of ground here, and this should kind of give you an idea. And I'm kind of glad we went off into these other directions and possibly did more complicated things, because it is useful training. You see, you got the whole, got the grand tour basically, the deluxe tour of the subject. So you can try a few more examples. Don't spend time doing hundreds of examples. Do when you solve something for practice, do it with quality rather than with quantity. Do a few, but in a very methodical manner, using the proper theory and steps like that. So even to write a page like this, it doesn't take 10 minutes to write this actually. But do it step by step in a sort of disciplined manner. So then you'll learn from it and you'll gain confidence. You'll see that if you do everything in a disciplined approach, you don't have to like wander all over the place. Things move in a very predictable and guaranteed direction with a high probability of success. Okay, so don't get too scared. Just practice all of it. Make sure you go over the theory. Really understand how what the theory is and how it applies and stuff like that. And then above all, get enough sleep. That'll have a bigger impact on a test than countless hours of studying. Okay, everyone. So I'll see you tomorrow morning then.
Thank you.
Okay, sure. Okay, bye-bye.
Thank you.
Yeah, have a good night.
Thank you.
Bye. You're welcome. Okay.
Kunjar, I have one more question.
Yeah.
So in like the answers to the problems, it'll say like a negative like force value and then says attractive next to it. Isn't the negative like it implies that it's attractive force, right?
Yeah, yeah. Often, like in Coulomb's law, if you put a sign for the Q1 and Q2, if the signs are opposite, the whole thing will be negative.
Okay, but like if I had written like negative 300 Newton per coulombs, or sorry, just newtons, and then ask for the direction, do I also need to write like attractive, or isn't that implied in the negative value?
Then it's if you want, you can put in parentheses attractive.
Okay. Okay, I just saw that it said a negative value on the answer sheet.
Yeah. I think that's what the negative is. But when you're doing vectors, there is no negative and positive. There is no such thing.
Okay.
A vector doesn't have a sign. A vector cannot be negative or positive. Because it has a direction, is more complicated than that. It has component, and they can have many different combinations of signs. That's why you have 4 quadrants. You can have plus, minus, plus, minus, and minus, minus. So it's not there's no such thing as a negative vector.
When it comes, hold on, sorry, Izzy wants to say hi.
Hi, how are you? How's everything going?
I missed your class. Ella told me you were teaching her section, and I was really excited for her.
So are you what are you doing now? Are you taking 202 now? No, you took it earlier.
I took your 201 and then 202, and then
Last
I
year.
actually graduated in December. So
Oh,
I'm
yeah.
working and studying for the MCAT. So
Okay, well, good luck on that. Yeah.
thank you. We both take it.
We take it in March.
Yeah, we both are taking it in March.
Okay, well, good luck for that. Yeah.
Thank you.
Thank you.
Nice to see you. Sorry
Yeah,
to
same
interrupt.
here. Okay.
So if it were just 2 charges, though, the direction's not as important, right? Because it's on the same plane or on the same like.
Right. So as soon as you have 2-point charges, they have the same. So a direction has 2 parts.
Mm-hmm.
A direction, there's something called a line of direction and a sense of direction.
Okay.
So the line of direction is the same, whether it's plus minus or plus plus. It's always the same line of direction. But the sense of direction, whether to the left or right, that can be opposite.
Okay. So the direction of just 2 is just you'd say attractive or repulsive or just have negative.
Right. But if it's a vector diagram, like if I give an example like this, this is a minus q over here, and there's a plus q here. Okay. What's the direction, the theta for f on q plus q is what? Suppose this is the question.
Okay.
Okay. Then really a complete answer is not plus minus or attractive and repulsive. This is going to get pulled in this direction. Now you have to move the vector so that the tail is at the origin. This is that force, right?
Yeah.
And then this angle will be what will it be? 45 plus 80. So the answer to this will be 225 degrees. This is the correct and complete answer. Not just attractive, repulsive, or plus minus. This would be the angle if you're trying to do it vectorially. What's the vector
And
angle?
sorry.
Yeah.
And that would be this. This is a case where you do the x component and the y component, and then use that angle.
Right. Now you could, but that's the formal machinery, which it doesn't require you to think. But if you want to think, you can think. This is going to get attracted this way, and then this is the line of the force, and the direction is as shown, right? And then
so the direction is 225 degrees.
Yes. So let's say I give you the coordinates of the. This is at the origin, 0, 0, and I give you the coordinates of this charge as 5 meters and 5 meters. Suppose I gave you that. Okay. So in this case, this force it's on 45 degrees. How do I know that? Because the x arc tangent of y over x is arctangent of 1, which is 45 degrees.
Okay.
And so this is 45 degrees. But that's not the angle. The angle is you have to bring the tail over here. So now you go counterclockwise, and it brings you to 225 degrees. You see how everything fits in?
Yes, but the answer is 225 degrees.
The answer in this case would be 225. Right.
Okay.
So you could still have this may not be 5 and 5. This could be 7 and 3 or something like that. Then that angle won't be 45. Doesn't matter. You'll add that angle to 180 degrees to get this thing.
Thank you so much.
Sure.
I appreciate staying a little bit longer.
Of course, that's okay. All right. Okay. See you in the morning, Ella. Okay, bye.
Bye.
Bye.